Hi, this is problem 513. So, for part A, we want to determine the rotational inertia of the rod and block system at the top of the diagram. Rotational inertia is a measure of how difficult it is to get something into motion. Looking at our equation sheet, we can see that the moment of inertia, I, is equal to the sum of the mass times the length it is from the central axis squared. This makes sense because the more mass something has, the more difficult it is to get it moving, and the farther away something is, that also makes it more difficult. So looking at our diagram, we see two blocks of mass m, and they're each a distance L away from the central axis. So we can just plug it into the equation and sum up ml squared plus ml squared. This will give us a total of 2 ml squared. For part B, we want to find the downward acceleration of the large block. First, we can see that the block is not in free fall because there's a tension force pushing it back up. As we use the equation F equals ma, we can see that the total downward force minus the upward force, which is tension, is equal to ma. Because our mass is 4m in this case, our full equation will be 4m times g minus the tension force equals to 4ma. Next, we can proceed to find the tension force by using what we know about torque. We know that torque equals to I alpha, and that torque is also equal to the tension force times the radius. Setting these two torque equations equal each other, we see that torque equals to the tension force is equal to I alpha over r. Substituting this new expression into our full equation, we have I alpha over r equals 4mg minus 4ma. We also know that angular acceleration times the radius is equal to the linear acceleration. If we rearrange this equation, we can see that the angular acceleration is equivalent to the linear acceleration divided by r. We can also plug in the moment of inertia we found from before, which is 2 ml squared from part A. Substituting all these new expressions in, we see that we have this equation right here. Now we have all we need to solve for the linear acceleration. Using some algebraic manipulation, we find that acceleration is equal to 2g r squared over L squared plus 2r squared. Problem C is a problem that deals with the conservation of energy. You may have studied potential energy and kinetic energy in the past. As I hold this water bottle up, it has potential energy due to gravity. The equation for potential energy is the mass times g, which is gravity, times how far it is off the ground. If I drop this water bottle and let it fall all the way to the ground, that potential energy will be converted into kinetic energy, which is 1/2 mv squared. Clearly, the higher I let it fall from, the more kinetic energy it will gain. So looking at our diagram, as the large block falls a certain distance, that same amount of energy is transferred into kinetic energy for the two blocks, the two small blocks. Because these two blocks do not change in height, it is a pure transformation of potential energy to kinetic energy. Thus, the exact same amount of potential energy is converted to kinetic energy, and our answer is equal. Now, as you can see, the problem has changed slightly in part D. The strings are longer, meaning the two small blocks at the top are not as tightly attached. As we let the large block lose potential energy, that same amount of energy is being converted into something else, such as kinetic energy. However, in this case, it is not a complete transformation from potential energy to kinetic energy. As the small blocks move faster and faster, they also gain elevation, as any spinning object would. For example, as I spin this earphone slowly, it only goes up a certain height. If I spin it faster and faster, it rises in height. Because the blocks are also gaining potential energy, it has less kinetic energy to gain. Because there's only a certain amount of energy that the large block lost in its potential energy, the other end of the system can only gain so much energy. Because some of this energy is converted to potential energy, the rest is converted to kinetic energy. As a result, the amount of kinetic energy gained in this new system is not as much as the kinetic energy gained in the previous system, where it was a full transformation from potential energy to kinetic energy. As a result, these small blocks will have less kinetic energy.